Hello all and welcome back to this course on digital systems. So in the last week we looked at the meaning of a logic 1 and a logic 0 quite elaborately, right? In the sense we looked at what does the logic 1 mean in terms of voltages and what does a logic 0 mean in terms of a voltage again. So we discussed that there is a certain range, from 0 to VIL. So for example, logic 0, any voltage, right, to a logic gate if is greater than 0 or less than or equal to VIL, okay, or logic 1, the input must be greater than VIH and must be less than or equal to the supply voltage, right. So this is for any arbitrary logic gate. I used the inverter in the last case to take you through the transfer characteristics and so on, right. So, so having established the physical meaning of these logic levels, we can now simply treat and this voltage range as 0, this voltage range as 1. So in the rest of the course, we will only be talking of ones and zeros, right, in various forms, in terms of the truth table, in terms of mathematical operations, everything we will be talking of ones and zeros, but at a voltage level, this is what we will eventually mean, okay. So in this week, I plan to get into the mathematical framework. So the module 1 of the course, which is basically the mathematical framework. Right. So the logic 1 and 0 also have a very specific reason why that works mathematically, and this week we will discuss that in great detail. So again, to let me refresh your memory with respect to what we had discussed in the electronic systems thinking course, right? And this had to do with the representation of an integer. So from the ADC we got an integer and we wanted to represent them as ones and zeros, because ultimately the computer is going to now understand ones and zeros through these voltages, through these voltage ranges, right? And therefore any integer that is given to us, we must be able to convert it to a binary representation, okay. And it was in this context that I had discussed that suppose you have a weighing scale like this, not a weighing scale, a weighing balance, right. So I have something like this, right, and there is a central point at which you can hold it, okay. And now I am going to place an object here, okay, which is anything between 1 kg, right, to 15 kg, but only in integer steps. So it could be 1, 2, 3, so on up to 15, okay. Now you do not know what the weight of this object is, and what you are only given is, let's say, 4 different weights, each of 1 kg, okay. This is 1 kg, 1 kg, and I have 4 such weights with me. Now I have to figure out what is the exact weight of this unknown red object that is placed on this side using 4 such 1 kg weights. So we had discussed that the one way to do this is, first of all, if you are given uh, you know not just 1 kg weights, but you are given 1 kg, 2 kg and so on, then you had to go in powers of 2 in order to be able to measure every integer between 1 and 15, right. Of course 0 is very trivially achievable, right. Now in order to use only 1 kg weights, we said we have to construct a very special balance which is like this, right. I have here, okay. So effectively if this is distance x, right, then this is also distance x, right, on which I can place a 1 kg. Then at 2x I have another balance, right, and let me move that here, this thing here, okay, and I have then of course, so this is another x, okay, then I have another at 4x, okay, I need to have a balance like this which is going to sit here, okay, and from the center this balance is going to be 4x, okay. Then I have another thing all the way quite far away which is going to be at a distance of 8x, okay, the last one is not to scale, so I am saying this is another 4x, okay, in terms of distance. So what happens is if I place a 1 kg block here, the effective weight that is going to see with respect the effective torque if you wish, right, or the moment, right, in physics parlance, that would experience, the weighing balance would experience on the right hand side is going to be 2x into 1 kg. Now on the other hand, if I placed a 1 kg here, right, and I'll just take this off, then it would experience a moment of 4x into 1 kg, right. Likewise, on the last thing if I place it, it would experience a moment of 8 into 1 kg, okay. So now in order to identify what this unknown weight is, what would you do? We would start with, let's say, the largest possible weight that I can measure with just 1 kg. I place it on the last balance. So let me let me assign some numbers here, okay. I am going to call this 0, 1, 2 and 3, okay, on the right hand side, and because it is on the right hand side I will call it R0, R1, R2 and R3. So I place one of these 1 kg blocks on R3 and I see if it is heavier or lighter. Now of course it could be equal, right. If it is equal, then I will just say the weight of the unknown object, red object, is just 1 kg into 8. So it is an 8 kg block, okay. But the block that I have placed on the left hand side, the red block, could be heavier, right. Now if it is heavier, then what I need to do is I need to go ahead and now place another block here, okay. So the total weight that is appearing because of the moments on the right hand side is basically it is 4x into 1 kg, okay, plus 8x into another 1 kg. The net weight because of these two blocks is going to be like this. Effectively, it will be 4 plus 8 equal to 12 kg, even though I am placing only a 1 kg block on each of them, right. Now you look at the weighing balance again. Suppose it is equal, then the weight is equal to 12. Now suppose it were not equal, okay, then what do I do? Then I need to say, let's say this time after I placed the 1 kg on R2, let us say that the right hand side was heavier, okay, in which case obviously I cannot be placing the block 1 kg block on R2. Therefore, I will take this off and then place it on R1, okay. Now if it is placed on R1, then the net weight that I am going to see because of 1 kg on R3 and 1 kg on R1 is going to be 2x, right. This thing will be 2x into 1 kg plus 8x into 1 kg. Okay. So, effectively it is like 8 plus 2. So, it is 10 kg as opposed to 12 kg, right. Now, let us say that the red block this time happened to be in the earlier case the red block was lighter, let us say this time it is heavier, right. So, what we know till now, right, what are the, we did 3 weight measurements, okay. So, I will write that down here, step 1, okay. We did 3 weight measurements. Step 1, we compared the weight against 8 kg, right, and the weight was greater than 8 kg. So, this much we know, right. In step 2, we said the weight was, we added one more to R2, right, and therefore, the effective moment that we saw was 8 plus 4, 12, but we then saw that the right hand side was heavier. That means the weight is less than 12 kg. Okay. In step 3, what we saw is by placing the 1 kg on R1, right, what we are able to see here is that the left hand side, the red block is now heavier than this, okay. So, what we infer now is W is greater than 10 kg, okay. Actually, you look at step 2 and 3, you will actually know what the integer weight should be. It is greater than 10, but it is less than or equal to 12, right, and therefore, it has to be 11. So, how do you do that? We know that the left hand side is now heavier. So, I will place an additional block of 1 kg on R0, okay. So, because of this, the net weight in step 3, okay, step 3, the net weight is 8 plus 2 plus 1. There is nothing on R2, okay. This one is because of step 2 and this is step 1. Is that, no, this was step 2, right. This was step 3 and this step 4, okay. So, what we are saying now is step 4, the weight will therefore be exactly equal to 11 kg, okay. So, what we have effectively been able to do, right, is represent this information of the weight of the unknown red object as 4 1 kg weights with a certain weighted addition, okay. So, what we see here is in each of the balances on the right hand side, you can either place a 1 kg block or there is nothing there. This corresponds to the 1 and 0 that we know. If the weight is there, it means it's 1. If the weight is not there, it is 0, right. So, therefore, what we are now effectively we have done, right, is we took the unknown object W, okay, which was an integer, and we converted this, okay, in blue to, let me just go back, R0, R1, R2, R3, okay. I am going to write it in right to left for a certain reason, okay. R0, R1, R2, sorry, and R3, okay. So, R0 is basically saying, look, that if that object, so each R, for example, Ri could be either 1 of 0 or 1, okay. So, the effective weight W, okay, in red, I can represent it as R3 into 8 plus R2 into 4 plus R1 into 2 plus R0 into 1. Okay, and that's exactly coming out of the fact of the way this balance has been constructed, right? R0 is at distance x, exactly the same distance as the weight that is being placed on the left hand side. R1 is being placed at a distance 2x, R2 is being placed at a distance 4x, R3 at a distance 8x, right? So therefore, what we can do now is to rewrite this as R3 into 2 power 3 plus R2 into 2 power 2 plus R1 into 2 power 1 plus R0 into 2 power 0. Okay. Now, each of these Ri's effectively can take only one of two values, 0 or 1. Either the weight is there or it is not there, and therefore, these are essentially binary valued numbers. Okay. This is a binary number, and a binary number can take only one of two values, 0 or 1, right? And because they are binary numbers, they are also called a bit. Okay. So, in fact, because they are called bits, these R's are actually represented by let us say B0, okay, B0 2 power 0, okay, just to say that it is a bit. B1 into 2 power 1 plus B2 into 2 power 2 plus B3 into 2 power 3. Okay. So, I can write this as summation Bk 2 power k, k equal to 0 to 3, right. So, effectively any integer, right, if you follow this algorithm of placing the weight, on the right hand side, on the right extreme, and then if it is heavier, you follow a certain thing, remove the weight. If it is lighter, then you add another weight, and so on, right. If you continue doing this, you can represent any integer on the left hand side of the balance with 4 binary bits on the right hand side, which basically are these 1 kg weights, a combination of these 1 kg weights, right. So, this is exactly what I had mentioned in my initial introductory lecture as the binary number system. So, if you look at this, right, this is nothing but the binary number system, okay, where each Bk can take either 0 or 1, and you are doing a weighted addition in terms of the powers of 2. Okay. So, compare this to the decimal system, decimal number system, okay, where the number can be represented in the base 10. Okay. So, any number, if you take this W, the same W that we are talking about, it can be represented in terms of, let's say that the weight was 12 kg. Okay. What does 12 mean? It is actually 1 into 10 power 1 plus 2 into 10 power 0. Okay. Now, if I had more than 15 kg, let's say I had a 3 digit, I could have up to 125 kgs. Okay. What does 125 mean? It is 1 into 10 power 2, 100 plus 2 into 10 power 1 plus 5 into 10 power 0. Okay. So, this one is getting represented as k equal to 0 to let us say 3 or 2. Okay. Some number ak into 10 power k, where ak is 0, 1, all the way to 9, any integer between 0 and 9. Okay, so in the decimal number system, the moment you exceed 9, you go to the number 10, right? You will add an extra digit, right? On the other hand side, in the binary number system, because you are dealing only with 0 and 1, you go from count from 0, you reach 1. The moment you reach 1, the next number has to be 1 and 0, right? That's the equivalent of the number 2, right? So mathematically, both these number systems are equivalent and you can work with them as identical representations of the same number, right? Maybe not identical, they are different representations, but they are, maximum I can say is they are equivalent representations, and therefore I can do addition with it, I can do multiplication with it, I can do whatever I want with it, and the answers will come out to be consistent in that particular number system, right?